We are living in the golden age of earthquake science. Seriously, we're like on the verge of some major breakthroughs. First, scientists figured out the inner workings of Earth's most powerful and longest earthquakes. Then they mapped the locations of millions of tiny quakes across California. And now researchers have discovered what might be the creepiest secret start of earthquakes. And it's not what you would expect. It's kind of like a horror movie where the monster is lurking just off screen before it pounces. But instead of a monster, it's rock. And instead of a pounce, it's a rumble. Like seriously, if your house starts shaking and you feel a lull, don't get comfortable because it could be the calm before the storm. Or more accurately, the calm before the earth splits open and swallows you whole. Well, maybe not that dramatic, but there could be a big quake coming. The new research was published recently in the journal Nature. And before we tell you about it, let's talk about something that could help you understand all sorts of science stories better. There are so many interesting things happening in the world, but how do you keep track? Some days when I scroll through social media, it feels like all I see are cat videos and arguments with strangers. If you're looking for something a little smarter, you need to check out Nautilus magazine. Nautilus is a science magazine that keeps you up to date on the most relevant topics that are being discussed today. They frequently have scientists writing for them who will take you into their world and explain it to you directly. Recently, they even had someone write about their experience on the James Webb Space Telescope. Plus, there are contributions from various authors, most recently on quantum computing and the future of human life. Nautilus has something for everyone, whether you're into space, technology, philosophy, or biology. What I really like about Nautilus is that they make science accessible. It's written for everyone, not just experts, so you can actually enjoy reading it and learning something new. You can read it on your phone while commuting, or use their app to listen to the audio version. And speaking of the app, did I mention that the first 200 people to sign up using my link will get 20% off their annual subscription and get 3 free issues? I thought you'd never ask. Go ahead, click the link below and give Nautilus a try. Thank you, Nautilus, for sponsoring this episode. And now let's get back to the show. Now back to those earthquakes. In the new study, researchers used 2 plexiglass sheets to mimic the movement of 2 tectonic plates sliding past each other. That's one type of fault. By placing one sheet on top of the other and applying pressure to the edges, they simulated the immense forces that build up over time along faults. Now, the researchers weren't trying to recreate the full dynamic range of an earthquake. Instead, they focused on the earliest stage when a crack first begins to form. In nature, these cracks start at a microscopic level within the minerals of Earth's crust. As the rocks are pushed beyond their breaking point, the cracks spread until they become visible and eventually lead to an earthquake. So in the lab, the researchers wanted to figure out how cracks spread in plexiglass, which is kind of like looking at the baby steps of an earthquake. They expected the crack to start in a straight line, kind of like a dropped glass rod snapping in half. But what they saw was unexpected. First, they observed a sort of wave moving through the plexiglass. The material around the wave compressed and then released its energy in a snap, and that caused the crack to advance. It wasn't a smooth process. Instead, the front of the crack looked like a series of tiny steps moving through the plexiglass. They dubbed this the nucleation front. It starts as a rounded bulge in the material that slowly pushes its way outward like a pebble dropped into water. This isn't exactly how a dropped piece of glass behaves. When they dropped the glass rod, it broke in a straight line, and that's because glass is brittle and breaks in a way that releases the most energy possible, almost like a perfectly executed Olympic dive. However, plexiglass is tougher and more flexible and doesn't release energy as quickly, so the crack spreads more slowly as the material tries to find the most efficient way to break. What's even creepier is that this front stayed roughly the same shape throughout the experiment. It didn't change much as it moved through the material, unlike a falling glass rod, which changes shape as it snaps. Researchers were surprised by this, since they expected the front to look different depending on the speed of the sliding plate. But the front stayed stubbornly round. Not only that, but it also maintained a constant width of about 1 and 2 millimeters, which is about the thickness of 2 paper clips. The fact that the front kept its shape and size suggests that the energy from the sliding plates was unevenly distributed along the crack. Instead, it formed these stationary bulges that acted like small barriers. These bulges also emitted waves that traveled through the plexiglass, just like ripples spreading out from a stone dropped into a pond. So why should you care about how a piece of plastic breaks? Because it turns out that plexiglass behaves a lot like Earth's crust. Both are made of minerals that are under a lot of pressure, and both can bend without breaking. So the slow, creeping earthquakes might start with this same rounded front that looks like it's pushing its way through the crust. In fact, scientists found similarities between the patterns on the plexiglass and real earthquakes. In both cases, the crack starts with a nearly invisible nucleation front. It grows until it reaches a critical size, and then the entire thing breaks apart in a matter of seconds. This is known as the main shock. The main difference is that in an earthquake, the nucleation front moves along a fault, which is a weak plane of rock. In the lab, the front moved through solid material. But scientists think that the two processes are similar. For example, both the lab-grown crack and the earthquake fault start out curved, and then straighten as they propagate. Also, both seem to have trouble moving around obstacles. In earthquakes, the main shock often ruptures along the path of least resistance, even if that means skipping over some sections of the fault. We know this because we can see how earthquakes skip across the surface of the Earth. Satellite images of the 2011 Tohoku, Japan earthquake show long, straight ruptures separated by gaps where the ground didn't move as much. These gaps are usually places where the fault cuts across a different type of rock or a body of water, things that get in the way of the earthquake's path. Similar things happened in the plexiglass. The researchers noticed that the crack often avoided small holes and seams in the plastic, just like an earthquake might skip over a river valley. This isn't the first time scientists have used plexiglass to study earthquakes. Back in 2019, researchers at the California Institute of Technology created a device that allowed them to apply stress to a model fault. They found that small earthquakes behave like traffic jams, which is weird, but true. Traffic jams and small earthquakes both start with slow, creeping motion, then suddenly lurch forward. The new study shows that this slow, creeping stage might be even more complex than we thought. It's not just a buildup of energy, but also a complex dance of pressure waves and crack propagation. And the best part is that all of this was done with just 2 sheets of plastic and some fancy cameras. This kind of research helps us understand the basic physics of earthquakes, even though it's done on a tiny scale. It's like studying the properties of sand in a small container and then using that knowledge to predict landslides on a mountainside. Of course, it's impossible to grow an earthquake in the lab. It's way too big and powerful for that. But by studying the basics of how materials break, we can learn more about the complex and sometimes creepy ways that our planet works. Now I'm going to go check on my foundation. Thanks for watching this episode. If you liked this video, hit that like button and subscribe for more fun science stuff.